Let's build the simplest possible universe.
Okay.
Just geometrically. We're going to start like that. We're not going to be so concerned about building our universe at first, because the general concern of how would you build any universe, it gives you a little more intellectual leverage to try that starting process, right? And basically, step one is the one everyone's been stuck at here. So to make step one easier, let's say we want to just describe the simplest possible universe. By possible, we literally mean self-balanced. So we mean there's no continual system, exterior system injecting into this to keep it going. There's no boundary conditions that some god needs to put in place or some other entity, right? It's a system that maintains itself, that defines its own self-balanced interaction. Okay, so the question then is, what is the minimal system, the minimal geometry or geometric balance, minimal way of partitioning some sort of field, breaking it up into different sizes of actions, such that doing that partitioning, that breaking up, collectively makes the fluid or the field twist completely around until it makes a closed loop. As soon as you make a closed loop, then you're going to make a closed loop again, and you're going to keep doing it over and over. So the question is, what's the minimal way of disturbing a fluid, say a three-dimensional infinite connected fluid, but it supports waves, okay? Somehow you can twist and locally affect it, and that will wave itself out. So if it supports waves, what's the minimal collection of waves that put together to form something that's self-closed, an action that wraps back on itself and becomes cyclic and cyclic and cyclic? Now note, it needs to be robustly stable, because we could just say, all right, well, going around in a circle is the smallest cycle. Yes, but we need a three-dimensional partitioning that makes a robust cycle. The circle going around can be disturbed by anything, and if it is disturbed, there's no longer the circle. So it's exactly not stable by itself. So we need a system that's more complex than this. It needs to be able to be three-dimensionally stabilized. No matter how you come to try to disturb it a little bit, it comes right back. It keeps itself. It's maintaining its own form and relationships between the boundaries of its form. So, circle's not going to do it for us. We need something a little more complicated. We're going to look in the literature, of course. As a physicist, whenever it's a math problem, I'm going to look to see what the mathematicians have already found out. And what have they found out? There is a minimal geometric form. It's called the hyperbolic figure-8 knot. So there's a three-manifold called a Gleason manifold. That's the minimal way things could try to be a persistent form, but it's not robustly stable. It's like the minimal circle kind of thing, but three-dimensional. The double cover of this minimal manifold is the robust one. It's the one that twists back and always twists into its own form. So the double cover is called the hyperbolic figure-8 knot. Okay? So this geometry is now, we're taking our infinite field, our infinite fluid, and we're twisting it under the actions that then twist that geometry into the shape of the hyperbolic figure-8 knot. More specifically, at this point I'll put a picture up on the screen. This shape represents the boundary between the inside and the outside partitioned balance that this minimal geometry forms. I know it's a mouthful, so we're going to say it in many ways. But if we stare at the boundary, first of all, if it's your first time seeing this shape, it was discovered in the mid-70s, so it's new in the field of geometry, despite being the minimal possible self-closed surface, so a wave action that forms a closed surface and makes this boundary. When that happens, we have an inside with a volume under action, so a very specific rotational momentum action balancing on the inside. But we have a volume on the outside that is countering that action. Countering externally, it has three directions to reach and counter. Internally, we have only two actions wrapping in together on themselves. So we have a split symmetry. We have an inside with two parts and an outside with three parts, three partitionings. Okay, so three different rotations on the outside compose this balance, and two different rotations on the inside compose this balance. The outside and the inside are separated entirely in the picture. The point of the balance is that the outside and the inside remain separated. However, there's an inversion symmetry between them because they define each other, they maintain each other. All right, so this is the minimal separation geometry that you can balance, the minimal way you can twist things together and form a closed volume that divides an internal versus external domain. Okay? And that's what you need in order to get a stable system that maintains itself. It has to divide something that stays divided. Perfect. So this geometry, this is our minimal universe, the minimal possible geometry we can expect to persist on its own once it forms. It might take a long time to form, it might be really easy to form, but once it does form, it persists. You can, of course, imagine there should be more complicated things, but let's focus on just the simplest one for a while. Okay, the simplest possible geometry. And let's break it apart into its different rotations. Let's separate it and individually talk about each one of its rotations so that we can then individually reference all 5 of its balances. Okay, it pulls apart into 3 external, 2 internal rotations. That's 5 in total. So let's try to characterize, let's try to look at this object long enough, really steelman its existence, right? We're going to stare at all of its properties, compare it, define its symmetries, and by doing so, we can then narrow down and specify its exact geometric balances. Great, so that's the process we're going to do. And the process is just going to start from looking at the picture and remembering this picture shows just the boundary between the inside and the outside of this balance. It's a still image, it's got cutouts. The cutouts are not part of the image, it's just so you can see inside, okay? But try to get familiar with the boundary here and remember it's separating the inside from the outside. So, to start to partition or start to specify how this separation is 5 separate balances, and to get at what those balances are, what they're doing, and to know them geometrically, let's write down the separation that we have 5 separate actions happen to begin with, 5 balances, okay? So we're gonna go balance 0. I'm gonna start at the bottom. At the bottom here, balance 0 is our first one. At the very bottom, we're gonna start with balance 0, just naming it that. We don't know what it is exactly yet, but we do know that if there's a balance happening, whatever the shape of that path that's at the minimal balance line, it must have an inside and an outside. And the balance we're talking about is the balance across that line. So once you've identified the boundary, the inside and the outside of the boundary is what we're talking about here, the balance across that boundary, okay? So our first action is gonna have internal. I'll just put inside. And it's gonna have an outside act that will, let's just write outside. An external act, internal, external act, better. And that balance, that matching of internal versus external, forms a balance that exists so many number of places in this system. Okay? How many? We know, we're just gonna put, it's gonna be some number, and very specifically, it's gonna be an n, where n is a whole number. So let's put an n here. Some whole number n, that's gonna be, because it's a balance, you're not gonna have partial of these balances. We're partitioning the system into whole numbers of these balances. We don't even know how many here, we just know that we're, very simply, it must be, if it's a closed system, something that has an internal and external part, and internal part, external part, and that those internal, external balances must have a very specific whole number of places they show up in the system. Great. Now, the rest of our partitioning, as we go up, go to balance 1, is basically already baked in for us. Balance 1. By which I mean, the structure of balance 1 we expect to then be also some internal component, some external component, and those balance across some whole number, let's put that n0. In fact, let's put these 2 partitions. It's more clear that way. Where these p's, p sub 0, p sub 1, have to be a whole number of some sort, okay? We haven't specified more than that yet, but it's gonna be partitions of a whole number. All right, we can do the same thing, so let's do it. Balance 2. Let's get an internal part, external part, and some number of places those balances are in play. Some number of times those balances are in play in this total system. Again, now we only have 3 more, and it's the same exact pattern the whole way through, but there's one inversion to remember. The inside versus the outside, they're not all hierarchically stacked. There's an inversion between the bottom 2 and the top 3. Okay, so balance 3 follows the same pattern. Now I know we're not being very specific yet on purpose about what the internal part is and the external part is. We're going to get more specific. First, we're starting to see what the whole structure is. Minimum partition balance, which means you assume the system is it decomposes into a fixed number of things and then go find and solve for the decomposed things. Okay? External again. And there's going to be a new number. Okay, I left a little gap here because balance 4, which is the last of ours, is the last external one, this equals 1. Okay, balance 4 is the projected final balance of all these actions. So every action is doing something, interacting, but the final projection has a center that the system collectively defines as the 1. It sets a 1 scale in reference to what? In reference to all of these actions. Literally, the system is referencing the 1. So this is the 1 of this balanced system. This is the minimum balance of this system. Okay, this is the 1. Wait a second, why is the minimum at one end and the 1 at the other end? Because this projected external rotation has a center. Its center is the stable projection of all this 5-part action. That's where the 1's at. It's not at the end, it's the middle of the last action, the balance of the last action, of the external action, which means it has boundaries. So I can think of boundary from it. It has a boundary that wraps on that side and this side of the balance. It's inverting, and it's inverting what? The inside. So the whole outside boundary of this balance line, balance 4, has 2 ends. It has 2 boundaries that are interchanging slowly, right? So this balance 4, we can now put boundary 4, and it'll have an internal and external part, the same pattern here. But this one will be the inverse. Let's write it in. Internal part, external part. And some number of derangements. Very specifically, this boundary over here, this is all for the hyperbolic figure 8 knot balance again, remember? This is the inverse boundary 4. So whatever the answer for the internal and external parts are, and for the number of derangements involved, then it'll be the exact inverse here. These are literally inverse actions, okay? Because they're tied together. So let me put down here, balance 0 has an internal part and an external part. We'll put sub 0. This one's going to sub 1, just to distinguish them. They're not going to be the same as each other. Right? This one's going to be 4, 4, 2, 3. Okay, just so you know, these internal parts are different each, and external parts and so on. Okay, that's our basic balance in as general terms as we can outlay it first, okay?
That's the balance of the hyperbolic figure 8 knot.
That's the balance, that's our partition balance, our general partition balance of the hyperbolic figure 8 knot. The first stage is to separate it into its actions and note that there's 2 inner balances that are making this thing up and 3 outer ones, okay? And that there's an inversion between the 2 keeping them. So the outer one has to invert to close against the inner ones. The outer 3 have to invert to close the inner 2, more specifically. Okay, Now, to make this more specific, balance for you. Okay, good. Oh, I did put in this up here. So this one is internal 4 minus 1 to the inverse power. Okay, so it's this one is the same as that one. This is the one case where they're matched up. Not the exact same, the inverse of. And the same with this. External 1 for inverse. Inverse. So it's the same equation, just written upside down. Framing on two sides. Okay, this is the general format. It shouldn't seem clear yet. What should seem clear is that we're just generally separating the inside from the outside, requiring that there's gonna be a balance, but that at each balance, the 2 on the inside and the 3 on the outside, they are made up of 2 parts. A balance has to have 2 parts to be balanced. So it has an internal part, because it's assumed to be a closed system, so it will follow a closed loop. So the minimum closed loop of our system, balance 0, is made up of an internal part and an external part, and so many of these balances are happening in the hyperbolic figure 8 knot dance, in the geometry, when that geometry is present. Okay. Next stage, how do we get more specific? Well, we could either specify an arrangement between these partitions, that, the balance between the partitions themselves, or we could specify that, hey, all these external actions, no matter what they are, compared to the internal one, they will be less complicated. Right? If there's a balance being maintained on a system by itself, an internal complicated action, there's a balanced line, the external expression of that internal complicated action will be less complicated. It'll be just a smooth rotation, like the averaged over expression of something, okay? So we can change all of these external expressions now to something much more specific. Let's do the first 2. We can say this one is just e to some rotation. We'll call it the 0th rotation because it's balance 0. Okay, so we know it now, it's just a smooth rotation, which means we went from not having any idea of what that action was to knowing it's a smooth rotation action, but we haven't identified what's the magnitude of it yet. Okay, so it helped, but it didn't give us everything. But what's really nice is that every single one is now in the same form. There's an external rotation with some magnitude balancing the internal action of balance 1 also, but it's a different amount. And this is 2, and this one has -1 could be put right there. All right, so we simplified our system a lot by assuming another simplification, by being more specific, realizing that whatever that structure is, this complex structure, it has a more complex on the inside than on the outside, and that outside one will always be the smoothest possible representation of the action. All right, so we will still have to solve for all of those actual rotation values, but if we can identify the internal actions of any one of these balances and the number of partitions that are involved, then we can solve for its rotation magnitude, for the rotation magnitude required to make that balance. Okay, first step here now is to find the symmetry maintained between these different partitions. Okay, if there was no symmetry there, then we might be talking about a system that's just chaotically decaying and falling apart. There has to be a symmetry between the partitions, because if one thing falls apart, if it partitions, but the whole system is closed, then somewhere else something has to be falling together. Okay, there has to be a closed exchange for how the actions are moving apart and moving together, and it's symmetrically closing. So, the inside, at the very, very bottom, we need to know something about, what are the partitions at the very, very limit of this balance? At balance 0, how many partitions are we talking about? How would we know? Well, we have 1, 2, 3, 4, 5 balances, okay? So if I put P naught, our partitions for balance 0, equal to the derangements of a whole number of actions. Since we have 5 actions here, a system of 5 actions, at the very bottom, we want to define our system, we want to define the derangements of our system as its full bottom distortion. Okay, the smallest distortion, everything's partitioned into its smallest parts, fully deranged. Then we're going to take its derangements and we're going to set that equal to this. So whatever this value is, it'll be the full derangements of those 5 rotations, the maximum way you can partition it up, which means actually we can solve for it specifically. We know its value now. P naught is going to be, if n is 5, the derangements for 5 things, the possible ordered ways you can take 5 things and make an ordered sequence, is 44. This is what the derangement function means. So we can now replace this specifically with 44, but I'm going to put this in here to remind you that what it means. It's the derangements, okay? Derangements of 5 things. So then we have to remember 2 things. N equals 5 and B equals 7. They're not hard to remember, but they do require remembering. In this case, I'm gonna list this number 44. I'm gonna list it as the derangements of n. Make it bigger and clearer. The number of derangements of our n boundaries. Okay, of our n unique rotations or partitions that make this balance. So n is 5. Exclamation point n, or derangements of n, is 44. So whenever you see this, it's just a 44. Which means now we have a system with some internal action, a smooth external rotation balancing that action over 44 places. 44 derangements maintaining an internal-external balance like this. What might this be? That's the big question now. We just need to solve for the internal balance of balance 0, and we will be able to now solve for the rotation, the external rotation that maintains that balance. But what internal balance is necessary in the minimal hyperbolic partition? The smallest possible balance we mentioned before would be a circle, right? But a circle doesn't self-stabilize, it's unstable unless it's countered by something. So we're going to set the smallest possible, the definition of derangements of the smallest balance. So this thing maximally deranged. We're going to set the geometry of that maximum derangement equal to a circle, okay, the minimal possible closed loop. And so we're going to put pi r squared for a circle, okay, the area closed in here. But our radius, very specifically, isn't the Euclidean r we're used to. Our r is hyperbolic. Our r is the hyperbolic sign. Okay? What's happening inside this is represented under hyperbolic geometry. Or you can think of it as you go inside, you're splitting and splitting in 2 different ways to maintain the balance. The internal parts are dividing. Okay? This is the stable line. Everything in there, you get more and more divided. What's the argument of the division? If we're under ideal hyperbolic balance, what does that mean? Well, what we need ideal to do, what we need balance to do are the same thing. It needs to come around and close on itself. The only way you can have an ideal split is half and half. That's what ideal means. But if it's an ideal squared split, it's half and half. Half times half. So we're going to put this x, our argument, as 1/2 squared. But right here we have to put a little, remember, since we squared it, it's operationally, we meant it to be squared. We don't mean it to be 1/4 by itself. You can't, well, I want you to remember it's being squared here because the argument's squarely splitting. Meaning, this happens to also be equal to -1/2 squared. That's the same thing. I can't distinguish the two, right? There's a symmetry, and it's equal to, these two are also equal to this, 1/2 I squared, because I squared becomes -1 and the negative goes away and it's the same thing. Or -1/2 I squared. Okay, so the argument that we're putting in here for the hyperbolic split has 4-fold symmetry. Kind of an important little note there. I'm going to, from now on, just write one of them, but all of them the same, because all four directions are symmetric. It doesn't matter which way you approach, okay? So I'm just gonna write one, but remember they all are all there. Okay, so now if we put this argument in here, and we put this radius into our circle equation, then that's our minimal geometry for our internal part here. Let me write that down. We're now saying that this is going to be pi times a hyperbolic radius circle, right? So let's put sine h1 half squared squared. That's it. So we're saying we're defining the derangements of this balance, the full derangements, defining them, knowing that there's 5 actions, 5 rotations that are partitioning the balance, defining that derangement to be a balance that's minimal, a circle, but hyperbolically balanced circle, with some external rotation maintaining this balance, which we haven't solved yet for, but now we can solve for. There's no other missing variables. This is a 44. Those variables are all known numbers, so now we can solve and get the actual value for this, write it down. Now we have a constant of nature balancing this geometry, right? Constant of nature that specifically references this one balance and the external magnitude of rotation of it. Okay, so this one number references this balance, but it tells you just the magnitude of the rotation of the external expression of it. Okay. That's a lot of progress, because we're saying that we now have a partition description that's complete at the bottom. So our hyperbolic figure 8 knot is minimally partitioning this way, right? Its derangement at the bottom maintains this balance. So we should now be able to explain the rest. The more we get, the more the other ones are narrowed down, made more clear, because the whole system has to close. So any action you're doing somewhere has to be inverted somewhere else, right? Okay. So I have actually worked through these before on a video, and I'm going to do it more with another video. But let me just allude real quick here that we can follow the same argument process now and work our way out, knowing what the hyperbolic figure 8 knot looks like. We can go out in scale and define the internal balances, the close part of the inside, and whatever's left over then gets closed by the remaining pieces as we go out. All right. I'm not going to do that right now, because I'm going to instead sidestep from here to point out why, for people who are like, why is he writing all these numbers up here? I'm not a numbers person. This is why to become a numbers person. Really why? Because so far we've only been talking about trying to specify details of a geometry that has never been fully specified before. It's a new discovered geometry, right, mid-1970s, and some things have been specified, which have been revolutionary ideas, but we're going to more specifically specify. And now we find that when we specify just the first level of balance happening here, the very bottom full derangement of the system, under conditions that it's hyperbolically balanced and the minimal possible closed loop, okay, the number we get for the rotation here ends up being the number for the Planck time. This is a very serious and exciting. The Planck time is the minimum limit of time. It's the measure limit, not the measurable limit. It's the measure limit of time. There is no meaning of time below that number. And it's, I should actually get the right number at this. I never memorize, I always look. All right, Planck time, 5.39, 1247, and plus or minus 60 times 10 to the negative 44 seconds. All right, so we really want to focus on this for a second, because this number here is known this well, plus or minus 60 in the 47. It's our error digits, and we know the size of our error. Right? Okay, so we know this number out to this accuracy, and look, 10 to the negative 44 seconds. That's really small, but it's not zero, and we know it. It's not, we're not just projecting this or making up some fancy thing. There is something in nature restricting time, cutting it off at this minimum limit. There is no time coherently even frameable less than that. Why? Nobody knows. This is one of the fundamental mysteries of our reality, of physics, and it's not even getting any airtime in physics because literally nobody knows what to say about it, right? It's not that physicists don't agree, it's there. But why is it there? If there were to be a minimum limit of time, you would expect it just to be zero, meaning there isn't one, right? You could always do half of that time or half of that time. It should be infinitely divisible. But here, we're saying in nature it's not. There's a minimum cutoff for some reason. You can't divide even the most divisible thing, time. It's the most divisible thing. You can't divide it past that. Interesting, confusing, exciting. Why? It gets a little more exciting when you realize, when you characterize the minimum possible geometry, the self-balanced geometry, the simplest one that can actually be formed, its minimum expression characterizes this boundary. The Planck time, remember, the most divisible, the thing that's partitioned the most, represents the full derangement of the hyperbolic figure 8 knot. It's the actual minimum boundary of the 5-part boundary of the minimum the 5-part minimum geometry mix of boundaries. This first boundary characterizes numerically the precise value and precise power of our known value, which means even more. It now lets us predict its true value to any significant digit. It's not, this is a measurement that's characterizing how well we know it. And this is the only way we've known this number so far, through the measurement, okay? This characterizes our knowledge of it. Now, it turns things around. We can now project this number to any digit. We know where it's coming from. It characterizes the minimum boundary of the minimum self-persistent geometry. It's a beautiful, beautiful connection. And if it were just that connection I had to show you, that's worth pulling everyone on the planet aside from all the little chitter chatter that people are getting distracted by. This speaks to the core of humanity, of our biggest physical mysteries, of our biggest intellectual mysteries and philosophical mysteries. And this really, we can open up an investigation that we've had closed now for at least my whole generation. Something that we don't talk about because nobody reasonable had anything new to contribute, right? It's not that we don't have smart enough people, but nobody knew what else to contribute. We just got a new paradigm here. A new paradigm where the minimal geometry, this minimum condition of the minimal geometry, characterizes one of the fundamental mysteries of our reality. The one which we held before as the mysterious minimum boundary of physical reality, of the 5 physical measurements we can make of reality. We can only measure things of time, length, charge, mass, and temperature. We can't measure anything else, with the caveat that you can make mixtures of those, right? Everything fundamentally we measure is a measurement of just time, length, charge, mass, and temperature, or a mixture, a combination of those. There are no other things to measure. We've found nothing else to measure so far. So if you can explain those 5 dimensions, the why they're there, and why they have these weird boundary conditions that we have no story for, you're really on to something. So far, we just found that the first, I mean, you can plug this into your computer, right? Go into Wolfram Alpha, type pi, parentheses, SINH, parentheses, type this in just like you see it, and put an X for anything you don't know how to type.
What's that website again?
WolframAlpha.com. Free. It's like a calculator, but it does way more than a calculator. I really recommend spending time on it because it's a source in which you can ask questions that you have no idea what the answer is. No idea, but you know how to ask the question. There's a whole category of questions like this. And Wolfram Alpha gives you a tool that will catapult you into an answer you couldn't have ever come up with, something you've never been exposed to before. It finds anything in the world that's already been related to that conversation and relates it for you and shows you the structure of the relationship. It shows you derivatives and integrals. Any math question you can think to ask, you can also try to ask it in English. It's trying to figure you out. So it's a worthwhile tool. I highly recommend it. I'm not getting paid to say that. I think it's a human tool. It allows you to ask a question, and it then gives you graphs and pictures and equations, and then you can start associating what those things mean. right? And building that intuition is very, very important. It's like learning to read. It is learning to read. It's learning to read more language, the language of geometry, okay? All right, well, things get much more exciting. You wouldn't think it's possible, but things do get much more exciting because there's not just one Planck boundary, there's also the Planck length. That's another 1.616, I have to get the whole number to write down, but times 10 to the negative 35 meters. A different dimension entirely. Dimension, a different, completely unique expression of the balance. They could never be confused. Okay, it's a different, unique expression. The Planck length's boundary ends up being characterized by that rotation. Okay, I mean, this is, I'm not just saying close. Oh, I didn't actually show the projection of the whole full number. Let's do that real quick. Okay, there we go. Using this value, or let me just write down the number for that value. So our external rotation for the very bottom boundary, that first balance, the zeroth balance, is gives us a value of 5.39 1258 368. All right, you can see 5.391247 plus or minus 60. So these are right, plus or minus 60 and 1258. Totally within the error bars. It's not even, it's dead on, right in the error bars here, okay? But this number now tells us what the true numbers are. We can then replace this and say, all right, well, we don't have any error in this one anymore. We know what's going on. Why? Because we know what it's referencing. It's a minimum boundary of the minimum possible geometry, and it's under this very specific minimal geometric balance. So we know it's precision, we know it precisely. This characterization, this partition balance that we're characterizing, turns out to do the same thing for all of the Planck constants. I'll speed that part up because I don't want to focus much on this. I want to get into where it goes. But remember, what we were really trying to do at the first was characterize the simplest possible universe we could. We wanted to invent a balance, a wave action balance that closed on itself under minimal conditions. The simplest one that would do that, the one that makes the least distortion, okay? And when we found that, well, geometers have already found this shape, it's a hyperbolic shape, and it was a surprise to find that you could have something that was hyperbolically emitting, but that it then emitted a closed two-dimensional surface. That emission creates a closed two-dimensional surface, which means now you've separated the domain permanently. Any closed two-dimensional surface is a separation. You have an inside and an outside. Beautiful, it's really beautiful, but that minimal geometry characterizes all of the Planck constants at the same time, and all of them to perfect precision. None of them are like out of the error bars at all. They're all perfect, which means we have one simple geometry explaining all of the minimal boundary conditions of physical reality, the minimal boundary conditions of persistence. The simplest possible interchange of boundaries that will continue and continue and continue. Okay, so this is our minimal expression of persistence and a characterization that's geometric of our minimal boundaries that are persisting. That's a huge leap of comprehension. Now we know that the 5 boundaries of reality are persisting in a system that's projecting 5 things. It's always partitioning 5 ways, which collectively close, some to nothing, but individually do something. So if you're in the system that's balanced by that, every one of those expressions is something unique. It's projecting your reality uniquely. It's a unique thing to investigate, right? It would not be confused with the other thing. Why? Because each balance has an external expression that's a different value, first of all, right? They're different magnitudes, but they're also balanced off of different internal balances. They're genuinely, in both ways, unique. You can't confuse them. However, they're all collectively part of the same system. They literally are the minimum system. All right, why is this? Well, obviously, I think it's obvious why it's exciting. But we can go much further from here. So far we're able to predict all the Planck constants, and I'll put that up on the screen in the video, so right now. With precision, we have boundary conditions for a minimal geometry that match the boundary conditions of our actual universe that were mysteries. Great. In physics, the way we usually proceed is we define a system by setting out what its boundary conditions are. We define them, or we have them given, right? And honestly, that's almost always the whole job. Once you've specified the exact boundary conditions of the system, the rest is implied. That was doing the work, right? That's what it means to understand the system. So we now understand a minimal geometry whose boundary conditions project the system we're most interested in. And beyond predicting numbers that no one's been able to predict before with perfect precision, the numbers that no one's really been directly focused on trying to predict these. I think everyone's been so confused that they haven't tried at all. But I guess no one's trying to predict the masses of the fundamental particles anymore either. But certainly there was an era of time where that was understood. Central mystery of humanity, central mystery of our physical reality. What are these masses doing? Why does the electron have its specific mass? Why is it that number versus another number? And why is it even there to begin? Like, all the questions are still there, right? What progress have we made since 50, 100 years ago? How much more do we know about why the electron has its mass? None. I don't think anyone's even studying this, honestly. I'm pretty sure no one is. I know no one's getting paid for it. But there was an era in which it was recognized widely that solving the pattern of the masses of the fundamental particles of matter, figuring out geometrically why they are what they are, how they got those values, what those numbers actually represent, that was considered, if we can get that answer, we'll have the biggest cheat window into reality that we've ever got. We can lift up the corner of the veil and understand a greater leap of comprehension than we've ever had, because that's a huge boundary no one's been able to even penetrate. We've basically given up. It didn't go away. It doesn't get to go away without being explained. It's still the partition parameters of the mass of reality. Mass only shows up in 17 possible ways, and it likes to show up mostly in the form of the electron, or the form of, I'm going to put a plus sign here for proton, because we have a Planck charge, that's that symbol, and we have a Planck mass, that's this symbol. So M sub P for me is going to be Planck mass. We can put plus sign to remember there's a positive charge, the proton, okay? And I'll put neutron for that. But these three masses are basically the most important partitions of mass. But what does that mean? What mass? What is the mass to begin with? That was always the problem. That's why we were stuck. We could say, yes, we've measured, we could write down these numbers, which by the way we know extremely well, the best of all numbers we know from measurement, versus knowing from geometry, which you can calculate out to infinity, right? Or you can always keep going. You can't ever make it to infinity. But these numbers, as far as measurements go, we know them as accurately as any number we've ever measured. We've measured them in CERN. It's not like we're using shovels for this, right? This is the best equipment we could come up with so far to try to measure the parameters of reality have given us these numbers and the constants of nature. But of the constants of nature and the 17 masses of the fundamental particles, these three particularly, we know extremely well. We know them about 13-ish significant digits, and 14 is the cutoff. So you never know more than that. Okay, what we really want to do is solve for why these masses and the other 14 have the values they have. We can look at the numbers and try to find the pattern, which I do recommend doing, finding patterns between things. But the biggest mystery we need to solve is, first of all, what's the mass? If you're going to explain how mass partitions, how it gets put into this size and this size and this size, then first of all, what is it we're partitioning? What's the thing that we're breaking up into those different sizes? That's the question we need to resolve. Because if you figure that out, it should be clear after that what these are, right? That's the real question. What is the mass? Here, we have a balanced system that's balancing 5 different balances. And balance number 3 is the Planck mass boundary. We have the Planck time boundary, the Planck length boundary, the Planck charge boundary, and the Planck mass boundary. And then we have the Planck temperature boundaries here. Okay? So literally all 5 Planck boundaries are being characterized with, literally, not just approximately, literally. All right, so if the mass boundary is just an internal balance and an external rotation, and the Planck mass is characterized by that external expression of this balance, and by its partition number, then now we have an answer for what mass is. Mass is one of the 5 balances maintaining the stage. Right? Without mass, the whole stage goes away. Time disappears, charge disappears, temperature disappears, space disappears. There's nothing. You need mass because it's one of the 5 balances, and this is a self-closed system. Every balance is needed. But mass is one of the unique ones. It can't be confused with the other 4. Okay, so the mass boundary itself, the balance line, which has an inside doing one thing and an outside doing another thing, that line in this whole domain of fluid action characterizes just the dimension of mass. It's the presence of mass, is that balance. And now we're saying that mass, that balance line, presents itself to us, because we're on a larger scale, we're external to it, because it's all smaller than us. The mass boundary is smaller than us, right? 10 to the negative 8 meters, definitely smaller than roughly 1 meter that we're comfortable with. The mass boundary gets partitioned. Right? So we have one mass boundary explaining the dimension of mass, its presence, its existence, its projection. Now we're interested, well, if it's projecting one thing, a balance, what's the ultimate chunks of this projection? Right? It's interfacing with other things, so it's going to be cut up as that wave goes around the other things. So which ways does it chunk up? Well, guess what? The 3 natural chunks, and let's try to make this clear. It's not that these 3 masses are 3 pieces of the boundary and then there's 14 more pieces, and when you add all 14 pieces you now get the boundary. That's not what's going on. Something even more beautiful, more symmetric. These 3 uniquely each describe that whole mass boundary. The whole mass boundary. The electron describes the simplest orientation of the Planck mass boundary. Okay, what do I mean by that? I mean literally, since we have a hyperbolic figure 8 knot on the inside, wind up in 2 here, these 2 balances are trying to unwind the hyperbolic figure 8 knot, external expressions of that. Its wrapped up energy slowly unwinds out one way and another orthogonal way. Well, this is the last of those 2, okay? And it's an external fluid balance that's wrapped up on itself on the inside. And remember, nothing on the inside ever touches the stuff on the outside. There's a division line. Because we have that kind of inversion balance, that means that the external shape, most naturally, since the internal shape is the hyperbolic figure 8 knot, right? The external shape will be 2 volumes of the hyperbolic figure 8 knot. It's just in a slit, so it has to be 2 of them that it traces and balances against what's going on the inside. Well, but this is units of mass. This is just a number, and that's just a dimensionless number like pi, right? And we need to reference it to what? Wrap it around what boundary, for example? The Planck mass boundary. Only one more step here. To realize that the Planck mass boundary, as it wraps around, it's moving over, it's an actual process, right? This external projection, the internal projection is a double cover. You go around twice, like a Mobius strip. You go around once, and you're now exactly opposite. You have to go around a whole nother time before you get back to where you really were. The same orientation this time too, while on the same side of the strip, okay? In this case, we have literally a projection of a double cover is being projected externally, and that projection has to balance against itself. So that's why it's doubled, but it's intersecting itself at the middle every time. It takes 4 of these actions because it has to go around a double cover, but 2 of them. Right? So the length of the path gets used 4 times. We have to use 4 of these Planck mass boundaries. So I get times by Planck mass, or 4 times, but I'm just gonna put it to the 4th power. So our mass expression is the minimal expression of the mass boundary. Notice we have a mismatch in units here because this is a doubled double cover. The expression you get is only one of the 4 that are there. There are 4 ties of this mass boundary maintaining the mass boundary, and one of those expressions gets, well, the one you probe is the one you interface. All right, externally, and because everything is a 2-part balance, we now have to worry about the other side. And the other side here is always going to be 1 plus or minus something, and here we're going to do hyperbolic sine of our full derangements divided by Bragg scale symmetry. So the derangements at the bottom here, we're going to be closing all of those that are last on our mass boundary. It's our last expression of that rotation. So we take them all, and we break it by, or we divide it by the break and scale symmetry to get you to the second scale. Remember, this is just a 7, and this is a 44. And, oops, close this, and this is inverse hyperbolic finite. Okay, oops, and then I need to do that. There we go, perfect. Where, well, let me do this piece by piece. This is the balance of the Planck mass boundary wrapped around a hyperbolic figure 8 knot, both of its external expressions, Mobiusly, so twice, okay? And this is the way we hyperbolically trivially terminate. So all this hyperbolic waving about has to close. So we have the inverse hyperbolic closure, rotated inverse, or the hyperbolic sign of our full partitions, a full number of derangements, but because we're going external, we now have an expression of those derangements that's diluted by the next scale. So the next scale of circular construction always goes from one circle, one scale. If you build the next scale you can from such circles, same size. Right? Not perfect, but 1, 2, 3, 4, 5, 6, 6 surrounding, and 1 in the middle, so 7 circles. So scale 2 becomes, a scale 2 of any circular construction is 7 more than scale 1 in every case. So our break and scale symmetry will be 7. All right, from this construction, from understanding that the mass boundary itself is just the balance, the third balance in our 5-part balance of the hyperbolic figure 8 knot, allows us then to immediately figure out what the first expression, the most natural expression of that boundary would be. And what we end up getting, if I didn't write these down, I could have just written all this out without telling you what it's going to be, but we get the electron mass. This predicts the electron mass exactly, just like the Planck mass, and the Planck time and all that, all the way out. It now becomes a geometric number. Some details. These should all be clear. This is the volume of the hyperbolic figure 8 knot, constant of nature, geometric constant of nature, dimensionless number. This is the Planck mass, one of the 5 that we define from that balance, right? From the hyperbolic figure 8 knot, minimal geometric balance. This is the hyperbolic sign, again, hyperbolic sign, derangements of our 5 rotations of the hyperbolic figure 8 knot, and of course that again. This symbol, we're picking very specifically to represent an arrangement of these boundaries that defines the inside to outside exchange, the balance between the inside and outside arrangement. And that's the Planck length compared to the Planck charge times by the Planck mass compared to the Planck charge, which I'm going to write, that's a weird way there. Planck length, Planck mass over Planck charge squared. Okay? This boundary is our entropy boundary. It's our terminal boundary. Every one of the rotations coming together here, making balanced systems, the systems that are partitioned apart have to eventually end up at our terminal boundary. They balance the other boundary. Okay? So every 2-part balance will have some sort of primary action and boundary and terminal action and boundary. But the terminal boundary will always be this very specific arrangement. And you might be delighted to go check when you have the numbers for the Planck length and the Planck mass. The digits, when you multiply them together, end up being the same digits as the Planck charge squared. Okay, go check it out. Okay, well, up for the first 7 digits, they're exactly the same. Very curious and interesting that the boundaries of physical reality have a symmetry built in, such that even if you took just the measured numbers that we knew for them, you take the Planck length times it by the Planck mass, the numbers here, multiply them together, and that equals the same number as the Planck charge squared, the number, not the power. Interesting. Okay, well, interesting. We know why now. We know this structure is balancing a 7 significant digit offset, right? Asymmetric scale symmetry balance. And we know that the break and scale symmetry is 7 internally. The internal break and scale symmetry between this scale and this scale is 7, which is why we can say, well, on this balance of 1, we can say it's equal to B times by the 5 rotations. So the number of derangements here will be 35 because of the break and scale symmetry. Notice now, since the break and scale symmetry internally is characterized fully just by 7, this boundary from internal to outside, external, is equal to 1 times 10 to the negative 7, which means if I do log base 10, or 2 times 5, so double cover, of the blank length, the blank mass, blank charge squared, that equals negative 7. Like, this is written into the structured balance of the minimum cutoffs of action, characterizing between 3 of the dimension actions that exist, 3 of the 5. Beautiful if that were the only thing you were to look at. Piece by pieces are beautiful, but all right, that boundary that's showing the symmetry, the inside and outside balance of symmetry, or break and scale symmetry that's going on. So there's 2 places here where our 7 is playing a role, inside and outside, of course. I'm not going to keep doing numbers on this because I want to pour through and I can show it on screen. Once we have our minimum construction of our mass boundary, once we know what the mass boundary is, and we put it in its minimum balance, then you can come along and say, all right, if I were looking at the surface created by this balance, I follow this balanced line that's traced out, and then we're to look at that balanced line perpendicularly, which is 2 ways you can look at it perpendicularly. Pick one. Perpendicularly, it's going to be falling apart, right? This balance is always under action, so it's maintained by falling apart, and the way it falls apart orthogonally falls back together. So if you look at the direction that shows you maximum tear, the way the thing is maximally partitioning or dividing, compared to the stable line of the mass boundary, you look at the division at 90 degrees, how it's pulling apart, then you're now looking at the mass of the proton. And in fact, you then characterize and define the exact value, predict the value for the mass of the proton. If you orthogonally look at the way it falls back together, you get the mass of the neutron. And here's where it gets really fast. These 3 things were supposed to be impossible to predict. These 2 patterns extend to give us all the allowed ways we can break up the mass boundary. All the ways we can partition it, or turn it into tiles. There are 17 ways to interface with this balance, and that's the same thing as saying that when you have a tiled 2-dimensional surface, so we have a closed 2-dimensional surface here dividing our world, right? There's only 17 ways that you can tile. There's 17 plane symmetry groups, 17 ways that you can put a shape, and then the same shape again and again and again and again, and tile the whole surface. And if the surface closes, that means you get to close on yourself, right? But just even if it's just plane, it went out to infinity. There's only 17 ways to tile that boundary. So if you know you have a fixed 2-dimensional boundary, then you know you have 17 unique expressions of that boundary. We have our unique boundary here, our minimum expression of our mass boundary characterizes the mass of the electron. Its orthogonal expression, the way it falls apart, this is the way it balances, this is the way it falls apart, and this is the way it falls together. The same boundary. Its 3 major expressions, the mass boundary, 3 major expressions of the mass boundary are the electron, the proton, and the neutron. And they characterize, define their values to infinite precision geometrically. More importantly, they tell us what it is. We now know, we can visualize and comprehend what's going on because we understand where mass came from to begin with. That mass is one of the 5 balances that are minimally projecting the stage of existence, the minimal stage of persistence, otherwise known as the hyperbolic figure-8 knot. We've already characterized every single one of these balances. We've partitioned it and characterized it explicitly, so we know exact answers for every one of the 5 Planck constants, for every one of these 5 rotations, okay? We have the entire picture mapped out, meaning the base geometry is explained. And the external expression of that base geometry has a charge boundary and it has a mass boundary, which are connected, okay? But the external expression of the mass boundary minimally balances into this form, which The same balance line, if you look at it, 90 degrees is this one, and if you look at another 90 degrees is this one. We have one balanced mass boundary, taking one very specific form that has 17 ways that you can express it, because that form closes a two-dimensional surface, and two-dimensional surfaces can only be tiled and can always be tiled by exactly 17 different partitions, so there's 17 different tiles. I want to talk a little bit about, let's see if this blue one really works. Yeah, good. A little about the connection now between the charge and the mass boundary. I know I haven't given any strong, I haven't given all the rest of the pictures to this yet, because I assume that you've been following some of my work and you already have access to that from the books, and I'll put it in video on the screen. But I want to connect this boundary and this boundary, the two external boundaries of this balance, the two external expressions that we see when we look in, when we try to probe the world with a microscope and look down and see what's going on in the world, see what's happening with the atoms and stuff. The mass boundary and the charge boundary here, they're not just something we can specify their balance, their inside and outside balance of in the external rotation. That's great. We can also specify the way that these two external actions connect, because we happen to know that it has to mirror the way that the inside connects, right? It's coming from that. They're not just magically there, they're literally projected from the inverse balance. So we know how they connect. And how? Well, the first step would be say, well, we know them to be basically under hyperbolic connection. So we want a very specific hyperbola. One, we want one modification to it. We want one of its parts to self-close, so to wrap around a circle. And then we want this thing, you can set it equal to anything you want depending on the scaling. We want something very specific here because we're using this arrangement to characterize it geometrically. We want that geometric arrangement to characterize two twists around the mass boundary. That's all we want it to do. And we want it to do it minimally. So if you were to twist, say you're pointing that way, and I want you to rotate, and now be pointing this way, that's what I'm going to call a twist, a quarter turn, okay? That's what I'm referencing when I say the word twist now. I want two of those, but I want them to be not this and then follow another one. I want one to twist this way and another twist out of the board, for example. It needs to be 90 degrees. All right, if I want two twists, I could write e to the negative pi over 2. That's one twist. And then I could make the other one negative pi over 2 here, and now it's orthogonal. Great. Because e to the negative pi over 2 equals I to the I, I'm literally just going to replace this in here. And there's lots of reasons. It's a preference. You can do either one, but I want our eyes to start getting trained with how imaginary components have relationships fixed geometrically that are useful. This one's one in here. We have two twists that have to be orthogonal and of this amount of 90 degrees, pi over 2, okay? And it's going to be around the mass boundary, right? The charge is twisting around the mass boundary. It's the dead point. Okay, when we set this condition up, we're just inventing this. We want the hyperbola that's modified by one of its parts being circular, and the other two that aren't, by the way, are exact inverses of each other, multiplicative inverses of each other. This one times this one is 1, right? Now I'm going to change my variable from x, just for preference, to je. Okay, it's an acrylic letter. It means the same thing as, it's just a variable. But it's going to be specific to me from now on. So whenever I'm referencing, well, we're going to solve for this equation, so it's no longer going to be a variable. That's fine. So yeah, when we put this into Wolfram Alpha, you type 1 over x or y, whatever variable you want to put in there, put in the same variable, write this equation into Wolfram Alpha. Okay? Literally just type 1 over x plus x, caret 3 for raised to the third power, equals, parentheses, I to the I. Literally write this out. And when you hit enter, it'll show you what it's supposed to look like, so you can know whether or not it understood that you read it right. Okay?
Well,
when you get this,
we should use x's for the j's.
use x's or y's or any, but stick to one letter. It's always the same letter here, here, and here. Yes. Any variable.
And the reason it's a je right now is because we're going to solve for je. It's no longer going to be a variable.
Yeah, it's no longer going to be a variable once we solve for it. So now that we've set up this equation, we can solve for it. We don't need anything else. We just need to do the solving. And how? Well, of course, we just go to Wolfram Alpha and we ask, what are the conditions? What are the actual numbers that make this true, that hold this balance? The same thing we were doing up there. We want to set the geometry and say, well, what's the conditions that maintain that actual geometry? All right, well, it turns out that there are 4 solutions to this, simultaneous solutions. The first one, we'll call je 1, okay? It's entirely real. Let me draw them. If I put them on a graph, this is 0 at the middle, okay? The first je 1 is right here. Almost 0, it's real close to it, okay? Je 2 is right here, like at 3.6. 3 back here and 4 here. This is our graph, our 4 different solutions. That's where they lie on the plane, okay? Je 1, if we square it, it equals the fine structure constant to every significant digit, not an approximation of it. It is the fine structure constant. Now, let's remember what we're even representing. We're characterizing a geometric relationship that binds one of the external boundaries or balances of this action with the other one. That's what we're doing. So we're saying these things are tied together hyperbolically, except this modification, and that hyperbolic connection exactly produces only 2 twists around the mass boundary. When we solve for the amount, the condition, the character that needs to play that role, the first character squared is the most mysterious number recognized in the whole of physics. The one that nearly everyone would want first to answer. The fine structure constant, right there, the first one. What about the rest? Are they just superfluous? We didn't need them because, wait, great, we got the best number we ever needed from that. Well, for a long time I ignored these until I recognized, hey, this is a partition function. These solutions tell you the 4 ways that the connection between the charge and the mass boundary. Imagine you were responsible for holding those boundaries together, but they're doing different things. They're going to do all kinds of things to you while trying to hold the boundaries together. The many things that can be done are really just expressed by these 4 partition constants. These are the partition constants between the mass and charge boundaries. Very specifically, they're not just general partition constants, they are the partition constants between the 3rd and the 2nd balances of the hyperbolic figure 8 knot. This construction with those 4 answers, those 4 partition values, if you multiply, let's add them together. Je 1 plus Je 2 plus Je 3 plus Je 4. Let's first, what would this even mean? And then let's find out what is it equal to. It's the solutions, all 4 partition solutions. When you know how the connection between the boundaries are being cut up, and then you add all of those together, you get 0. It's perfectly balanced, right? All the partitions themselves have to counter each other, so if you add them all up simply, they just cancel to 0. But watch what happens when, if I multiply them. Now we're taking ways of breaking up the charge and mass boundary, the solutions that tell us the way we partition it, and we're multiplying all the partitions together. Before we were adding the partitions and we got a perfect balance around 0. Now we're multiplying and we get 2 pi. We get that the product of these partitions is a circle. Really, really beautiful. So if we have the sum is 0 and their product is a circle, what might be their square sum? Right? There's something else to look for. So now let's try it different. Let's add the squares of each. So Je 1 squared plus Je 2 squared plus Je 3 squared plus Je 4 squared. And that equals, it's really beautiful, -4 pi. Now, Do you know what 4 pi references?
Sphere.
Yeah, surface of a sphere. And 2 pi, circle.
Circle.
Why negative?
Oh, good question.
Projective. You're pushing it out, not pulling it in, just a direction. Well, add a direction to it, right? So here we have a system whose partition parameters simply add to the balance that's most balanced, 0. And their product, together they produce the product that's a circle. But if you take 2 of them and intersect them first, and then add them up, instead of being 0, the perfect easy balance, they're not a 0 anymore. They project a sphere. Just by taking 2 things that if you put them together would be 0. Beautiful, right? So there's a simple balance, and what do we have to do to get that? How do we go from 0 to a sphere? We only squared each component. That's the only difference between this line and that line, right? So we used 2 of these arranged as squared, so each one is intersecting itself squarely, and then we get this. Okay, there's some numbers to be introduced here. There's a reason, exact reason for all of it. We're partitioning a sphere under 4 different sized partitions, right? 4 actions. And by the way, J3 and 4, well, I'll have to type on there for a while. Did I write those all right? Good. J3 and 4 are complex. They're all complex, but the complex part of 1 and 2 is 0, right? The imaginary part here, you notice, is not 0. It's not on this line. It's up here, and this one's negative. So they have reflective imaginary components. It turns out that if you were to write the real part of J1, which is the same thing as J1 in this case, but now add it to the real part of J2, and keep going. That still equals 0. And if I were to rewrite it, the imaginary part of each one is still equals 0. So if I sum them, their whole parts, they are 0. If I sum just their real parts, they're 0. If I sum just their imaginary parts, they're 0. It has 3 orthogonally balanced zeros held at the same time in this system. Why 3 zeros? Because we have 3 centers to maintain. Right? There's 3 things you're balancing against in the external world. Great. That's the world we were trying to partition, the external world. I skipped something here. I could have said also, the J1, our very first partition parameter, if you apply that partition, that way of breaking things up between the charge and the mass boundary, to the charge boundary, that happens to equal, well, let's see here, we have the charge boundary, which means what? It's balance 2 in our hyperbolic figure 8 knot. It's doing one very specific thing, but we're wrapping it externally now around the first solution of our hyperbolic vortex equation, and then turn the charge, the only charge, exactly into the electron. Kind of familiar? The mass boundary turns into the electron minimally. The charge boundary turns into the electron minimally. That is the expression of the charge boundary of balance 2. That's what it needs to be. That's what it turns into. And it minimally does so. Right? The mass boundary is more complicated. This one literally just takes just the partition amount of the hyperbolic vortex equation and says that's what we're doing to the mass boundary. And when we do that, we get the electron. Not even any other parts to it. It's really simple. Okay, we now have a system that externally balances its charge and mass actions, those things with those dimensions. They're wrapped very specifically into one geometric arrangement, which can be tiled into all 17 of the mass boundaries, the mass values on the mass boundary, or presents itself as the electron on the charge boundary. Literally the charge boundary is wrapped by this form, and its first expression is the electron. That's beautiful. Okay, so we're getting an entire theory of everything, and we haven't strayed from just this, the structure, the minimal structure that gives the projection of the dimensions to begin with, that would give us the form of time and length and charge and mass and temperature. So what we're saying is literally that the minimal universe, the minimal possible self-balanced geometry defines the minimal possible self-sustainable projection or stage or reality. It needs to be something that persists in order to continue to exist. And literally, because this is the geometry of minimal persistence, it is the stage of existence. Once it forms, it is a projection that continues to be. Now you can add many of them, intersect and imbalance and so on, but this is the minimal possible universe. A universe that has one boundary of time, one balance of time, and one balance of space, length and charge, mass and temperature, and all of those balances are creating the entire projection of one simplest universe, whose time boundaries are really small, doing lots of things, small partition actions that look exactly like this. And the next boundary is a little bigger, doing different things as we go up. The last projection, the top boundary, boundary 4 inverse, reaches to the last end of the entire reach of action in this minimal universe. That's the edge of the persistence. Okay? Outside of that, if there is anything outside of that, it's not part of the balanced system. It's not something we're even addressing. Okay, so by characterizing the minimum possible geometry more explicitly, the connections that partition the boundaries that are maintained in that balance, we literally partition a world that's under internal time and space balance construction. The internal construction between those two tells everything else what to do. So we're in a space-time constructed world that's externally inversely expressing in balances of charge, mass, and temperature. The construction of space and time is being received in the actions of time, mass, or charge, mass, and temperature, twisting against it, okay? So minimal possible geometry, minimal possible way of partitioning that geometry gives us the electron, the proton, the neutron, all of the masses, all the charges. It gives us the way we divide up the world so precisely that it predicts the actual values of all of those constants. Numerically, gives us deep core insight to what's going on. Primarily because we come from the step first, in which the dimensions of reality, the stage itself, come from this projected balance. That means that each one of those actions, each one of the dimensions making up that balance, intrinsically has a cutoff. It has a range in which it's doing its thing, because once you cross the range, across the next boundary, a different thing's happening. So there's a range. This balance from small scale until you cross the next boundary looks one way, and then it looks a different way, and it looks a different way. So it's scale dependent. It's heavily scale dependent, the whole system. The reason it wasn't so obvious to us that the structure of the world was balanced under scale asymmetry is because, one, the higher scales are hard for us to imagine. We needed to intellectually parse this to begin with. But the internal scale here, this is the external projection of the whole hyperbolic figure-8 knot. The fluid that's most externally still, that's doing the least, the most boring spot, right? Because an external projection, if you're rotating something, the middle of that wheel is doing the least, but it's still rotating. It's not doing zero. It's not under no action. I think we've introduced the basic ideas here, but if it's too much and too fast, we're going to be going over this many times. Try to take in any bit you can, because we're saying this is fundamentally, intrinsically important to the questions most pressing to conscious beings. What is the structure of reality? Why is it the way it is? Why is it show up the way we keep seeing it show up instead of other ways? What explains those persistent properties? We've now started from trying to explain the minimal possible persistent stage, the domain that wraps against itself and balances itself. That minimal stage gives us those answers. It partitions the world perfectly into those 5 actions that are all collectively acting together to keep the balance, to close the action so it doesn't go out to infinity, it stays localized, despite the fact that the outer boundary is 10 to the 32 meters out, it's still not infinity. Okay, so this is where we're at. We have one minimal geometry, the minimal geometry, revealed as the geometry of reality. It's the shape of reality, the balanced partition structure that keeps things persisting. It's the minimal way to have things being balanced under partition and persist. Right from this step, get the rest of it.
Solve all the rest.
Not just the rest of the hyperbolic figure eight knot structure, but all of its partitions, right? All of its predictions, the whole set of constants in nature, all the fundamental particles of matter in the charge and mass assignments, right? All of it. That whole fundamental structure of what is just this. And really important to remember, two-part system. Every balance that plays fundamental role here plays that role by being two things. It maintains two things across a boundary. Yeah.
And that was a big insight because we were
Real big
searching
insight.
for
Well, when we think of numbers, we think of them as a string of digits.
Right.
If that string of digits is composed of two things and you don't know, it's always natural to keep just thinking it's just a string of digits. That's not a composite
Right.
that's making it, right?
Yeah, it looks like one thing.
Yeah, until you see what the string of digits is actually composed of, and then, yeah. So, by which I mean, if that's confusing to some listeners here, this structure that we have in our balance, externally always, if you have an internal, external part, the external part will always end up on this one terminal boundary, which is the Planck length, the Planck mass over the Planck charge squared. So every time, there's no other boundaries that it ends up on. So we have the basic prescription for how to then solve. If you wanted to use this pattern now to solve for any constant of nature. Any constant of nature. Let's give that a couple of minutes. Let's actually do an example. Let's do two of them. We're going to do the electric constant, okay, and Coulomb's constant. So the prescription for solving any constant of nature is the same for every single case. Let's do it one step at a time here. For the electric constant, just the symbol here, okay, let me write out. Don't need this anymore. Let's make more room for this. All right, the electric constant, here's our symbol for it. And what we know about it, go to Wikipedia, type in electric constant, check, find what's its value. Okay, they usually report its value, I write it down for you. It is 8.85, 418, 78, 128, and the error is 13 on the 28. Okay, plus or minus, or sorry, times by 10 to the negative 12. And very importantly, when you're looking this up, write down the units too. Very important, because it's you won't be able to figure out the solution without the units. All right, the units are seconds squared, coulombs squared, over meters cubed kilogram. All right, that's the data that you have. And now we're saying we have a balanced system that will allow you to make sense of any one of its fixed actions. Because its fixed actions are an intersection of its boundaries. So we can solve for what is the geometry. What's geometrically going on when we get this number? When we say we're talking about the electric constant, what are we talking about? Here's the prescription. Every constant in nature is equal to a primary action, some sort of geometric action. So we're going to call it action A primary, okay? Just going to write that. Remember, it means some primary action that we haven't yet identified, and some primary boundary. So these two come together, some action on a boundary, okay? A geometric action could be like a circle, so it could be 2 pi as your action, or it could be a split, so it could be the alpha Feigenbaum constant. Whatever, it needs to be a geometric simple action. And action of partition, I should point out, this list of things that could be this are, you could use any combination you want, like multiply times, or multiply divide, kind of arrangement or squared of the jeux. Or pi, or the simple geometry numbers like that. But we're talking about, we want to use, we're describing the constants of nature directly in terms of its partition parameters, okay? So we don't want crazy geometric things going on. It's always just the simple partition geometries. All right, this is the first part. It's a primary action on a primary boundary. And there's some sort of reflected action, you could think of it, or terminal action connected to it. And this could be plus or minus. Depends on if the action's oriented in the negative way or the positive way. So 1 plus or minus here, some terminal action. So T for terminal, primary terminal, and I'm going to put boundary terminal. But remember before we said that the terminal boundary is that guy every time. So I'm not even going to put in the B, because you don't need to solve. This looks like there's 4 things to solve for, and there's not. In our prescription, this is really helpful. The terminal boundary is always the same thing. Now, we haven't specified the constant of nature. That's what I mean. This is a general prescription. No matter what constant of nature you want to put in there, this will be the terminal boundary. You need to solve for the terminal action, the primary boundary, and the primary action. So let's do a couple examples. Let's show you how, because there's no missing pieces once you have the data point. So in this case, the electric constant, we're going to put it right here. Electric constant equals some primary boundary or primary action and primary boundary. We can solve, pause. First step, stage 1 here. We already know this one, but we also know that its value is very small in power. That's critical, because it means we can ignore this entire contribution because it doesn't do anything out until here. It shows up there. Now it does do something after that, or at that point from there on, right? But because we're trying to solve for this, we can ignore this and know now that our accuracy is going to be here. Okay? Simple. Because accuracy of 3, 4, 5, 6, 7 digits is huge accuracy. Nobody's ever gotten a model that does that before, so we're not worried about that. Okay? If it was down to 1, then we'd say, yes, there's a big problem. But here, that means we're starting out, we set this equal to 0, pretend that that's 0 for now, okay? Which means we can ignore this whole part for now. And now we have to solve for the boundary, or we have to write down the boundary. In this case, the boundary is going to be the combination of the dimensions in the constant. So we look at the dimensions here, and we say seconds squared. What's the seconds boundary represented from in our geometry? Seconds are Planck time. So because seconds are referenced by the Planck time, and because coulombs are referenced by the Planck charge, and because meters are referenced by the Planck length, and kilograms are referenced by the Planck mass, in our system, in our balance of the hyperbolic figure 8 knot, the dimensions themselves tell us exactly what the primary boundary will be. If that's not completely clear yet, that means we know this is our prescription of the dimensions that belong to that constant. So we go to seconds, say Planck times squared, because it's squared here. Then we go to coulombs and say, oh, that's going to be the Planck charge, and it's squared. And then we go to meters, and we go to, oh, that's Planck length, and it's cubed. And we go to kilograms, and it's Planck meters. Oh, sorry, Planck mass. Okay, so our units here tells us that that's our primary boundary. So we're going to replace primary boundary, in this case, with just that. QP squared, LP cubed, and MP. Now, yes, this is scary, lots of stuff going on. But it was all written directly in the prescription here, the number. Literally, this entire construction is read just from that. So it doesn't take much to get used to, it's easy. And it's because we know that the dimensions themselves are projections that we're accounting for now. We're using them as the boundary conditions. So when we want to ask, what's the boundary that the action's happening on, they define it, okay? Once we've set this, now, since we have this value, put this number with its power, the whole thing, in here, in there, in the computer, right? And solve for the primary action. So you just ask Wolfram Alpha, what is it going to be? Remember that the things it could be, the things it's made up of, are going to be pi, one of the j's, right? One of our partition numbers. So look for these numbers specifically. Or in this case, it doesn't. It's this case. It's oh, is it 1? 1 over 4 pi. 1 over 4 pi. So pretty easy to solve for that one in Wolfram Alpha because you would recognize it. Well, if it says, okay, here's a few choices of things that it could be, and then 1 over 4 pi showed up versus all these crazy unintelligible things, you would right away recognize, okay, great, 1 over 4 pi. Okay, so we've solved for A, and that answer was now right after the first 7 significant digits, but we know it's the right answer because it's so simple. One of the reasons, right? So now we undo this approximation where we got rid of that, and we bring it back and say 1. The plus or minus will be determined by this value, by the way, now that this is done, so you'll find out, I think it's minus. And then we have to solve for the terminal action. Is there any work to do? No, we just then again plug it into Wolfram Alpha because there's no missing components. That's known. And everything else is now known, so we can solve for what terminal action on this boundary maintains this balance. And here's where it all falls back together, because so far it's perfect, just a balance, a geometric balance of boundaries. But that balance has to close here. So this one has to be another, you have to get another number that works. That's part of what we do in our partitions. And there's only so many numbers we've shown you so far that are about important, right? Showed you a b equals 7 and n equals 5, our 5 rotations, so the hyperbolic figure 8 naught, which give us the 5 Planck constants, and our j's, and pi, stuff like that. There's not that much on the table. So we need AT to be out of some of those. In this case, I'll check to make sure it's right. I think it's just 2 to the n over, n squared over 2 to the n. Yeah, in this case it's n squared over 2 to the n. Okay, and then even if you don't know what this means if you're putting things in powers and so on, you would recognize that, oh wait, we use the same n's that we've been talking about before? Yes, it's the 5, n is 5. This is literally 25 over 32, okay? But I'm not gonna write it like that because the 5s are the 5 rotations. But 32 is the same number we use for temperature, the partitions of the temperature boundary and so on. Okay. Cool, we've done one, we finished. By which I mean, when we put this number in here now, and then we erase the value we had for this, and put it as the unknown now in Wolfram Alpha, and say, okay, now what is the whole answer? It will spit out to any digit you want, the correct full answer of this geometric relationship. And we got the whole thing just because we knew that the hyperbolic figure 8 naught has these boundary conditions, and we knew that if there's a balance, it has to be a 2-part balance. And cleverly, that the second part is this digit shifted, this much smaller contribution. It doesn't show up to the 7th significant digit. Okay, so that allowed us to piece answer this thing, otherwise we would have been stuck. So really, really cool. The asymmetry of our system allowed us to get a 7 significant digit accurate answer. And if you're already right for the first 7 significant digits, that's a huge leap, right? And then we just solve for the second part. So in every case we can do this. I want to do one more to show a symmetry here. The Coulomb, no, what did I say? Coulomb constant? Yeah, Coulomb's constant. Okay, Coulomb's constant I will put right below it, I guess. Yeah. And let me write down its value. I guess I should write it over here. Just to have it on the screen. Well, not K like that. Kappa equals 8.98, 755, 17923 with a 14 as the error bars, and times 10 to the 9. Now, of course, you have to write down the units, very important in this case, right? So the Coulomb units are meters cubed, kilograms. Let's see how, when it gets noticed here. Meters cubed, kilograms, seconds squared, Coulomb squared. Notice anything about the units here compared to the units there? Exactly upside down.
Upside down, yes.
Cool. So now we know exactly what this part's going to be. I'm going to make it upside down. This one's going to be Planck length cubed, Planck mass, over Planck temperature squared, and Planck charge squared. Cool. We need to solve for the primary action of that balance. Now, that inverse balance, which is interesting because if it's an inverse boundary, the same boundaries but inverted, so it's the inverse relationship with the same boundaries, okay? And our constant out in front is 1. Nice. It's just that association between them. This is the inverse spherical projection, and this is 1. Interesting. But when we come here, we notice a different interesting. What do you notice?
Well, it's a plus instead of a minus.
Yeah, that's all that changed. That's all that changed. It's an inversion symmetry in 2 ways. These 2 constants of nature relate to each other by being something on the same set of boundaries. Both of these address the same primary arrangement of boundaries except inverted. And in one case, it's a simple arrangement. In the other case, that inversion gives us a 4 pi, a sphere. Okay? Same arrangement of boundaries. One side gives us a sphere. The other arrangement gives us just the simplest trivial case. And its reflection of these 2, which are tied just by this inversion and 4 pi to 1 symmetry, are also tied under sign inversion on the terminal boundary of the same action. Beautiful. We literally say this constant and this constant tie together a thing that's a minimal thing and externally a sphere under perfect inversion. Right? There's no leftover. These cancel. All right, there's an example. We can go through every single constant in nature this way. You list its number, right? You put it in here, and then you set this equal to 0 because this number is so small for now, so we can ignore this second component to the terminal component, and then solve for the primary component by knowing that the boundaries have to be defined by the dimensions of the constant. And the dimensions have to be represented in Planck values. So by turning the dimensions into their Planck values, then we solve for the primary boundary. We can easily just quickly check Wolfram Alpha at that point. What's the action that makes this work? If this wasn't obvious, because sometimes A is just 1, which you don't need to check at that point. But then once we have this, we can then get rid of this being 0, as we were pretending, and solve for the actual terminal action and find the inversion symmetries. Find the balance that's going, get more details from the internal structure. From what? By taking the data and applying it to the known balance, the geometry, the structure, and finding then what balance, what geometry actually addresses that. Right? And then taking it seriously, taking it real. That's what's going on in reality, because we've collapsed the whole picture to a simple, minimal balancing condition. Right? Something we can all wrap our heads around, something we can actually investigate further with and make progress in our comprehension and our intellectual growth. There's a lot here that's given, it's offering us a lot of anchors of comprehension. We can explain why the electron has its mass and its charge, and the proton and the neutron. And that whole story is the same story every time. Right? Those boundaries are all coherently maintaining each other and partitioning always only that way under this one arrangement. And yes, it's new, but let's remember it's the simplest possible self-balanced geometry. We're not talking about the complicatedest one, the worst one, or the most difficult one to understand. We're literally talking about the one that's the minimum possible self-balance. It's just the minimum one. It's the geometry of minimization. It's the simplest thing of persistence. Anything else requires being more complicated beyond this. And the simplest possible one partitions into the world we've seen, describing the same numbers that we characterize our world with identically. All right, I need to eat. All right, thanks for following, guys. Let's get this conversation going. We need more people investigating and looking here. We need more people on the planet actually looking at the hyperbolic figure 8 knot and realizing the importance of understanding things in terms of geometry, in terms of persistent balance, in terms of something that's not magical. Because when you realize in your head that the curiosities you have most fundamentally still in your head about what reality is, when you realize that it's not magic, that it's something investigatable, it's something you have to investigate, right? An answer to something that's It's supposed to be beyond your ability to find. Tells you something about reality that changes everything about the way you think. It changes how you define relationships. It changes how you act in the world. It changes what you're after. The intellectual awakening of any new idea, especially geometric, means you're now aware of a new option of a way to talk about things, a new way to frame things, a new way to hold things in your head that's telling you a story about yourself, right? If you can't frame reality clearly, then you can't clearly move about in it. But for the first time in history, we have a way to clearly frame the construct that balances the dimensions of projective reality to begin with, defining where they come from, why they're there, why they're still there, why they persist, and why, if those are the dimensions in reality, do all of its properties manifest exactly in these specific ways. We finally have that, which means we can now start to probe reality in a much more specific, detailed, accurate, on-purpose way, under the understanding that our probings, the manipulations we want to do, the changes we want to investigate and explore, need to be respective of the actual balances that are maintaining the dimensions. You disrupt the balance, you get rid of the entire structure. So understanding the balance is key to being able to now investigate the world in a much more crisp, precise, and honest way.